In this lecture, I want to discuss on a high level the technicalities or details surrounding the typical implementation of the shared pointer. I'll introduce the control block, which keeps track of the reference count, and I'll talk a bit about the weak pointer implementation as well. Okay, this is an example of the typical implementation of a shared pointer. We have on the stack a shared pointer instance, and as you can see, that actually has two pointers, so it holds two pointers. The stored pointers are pointed to the managed object or owned object on the heap. Then we also have a control pointer, which will point to something called a control block, which will also be a dynamically allocated object. Now again, this is just going to be a high level example, okay, but you can see in the control block here we have a use count variable. This is basically the reference count variable, so the control block again keeps track of the reference count. We also have a weak count variable. The use count or reference count again is going to keep track of the number of shared pointers that own the managed object, and the weak count variable is going to keep track of the number of weak pointers that refer to the managed object. Then it also has some pointer, I'll just call that managed pointer, which is going to point to the object on the heap that the shared pointer manages or owns. Now I would like to note that the control block is going to hold either a pointer to the managed object, as we can see in this example, or it's going to hold the managed object itself. That is in the case where you use the makeShared helper function, but we'll just stick to this example for now. The stored pointer in the shared pointer, in other words the pointer held by the shared pointer, is the pointer that we return using the getMember function, while the pointer or the managed pointer in this example in the control block is the pointer that will be deleted when the number of shared owners reaches 0, in other words when the reference count reaches 0, and it's actually going to be the control block that calls delete on the managed heap object. Following the destruction of the managed object, the control block will actually destroy itself by doing delete to this. Okay, so let's step through a couple of illustrations on how this would work. Let's say that shared pointer on the stack goes out of scope and gets destroyed. The destruct of the shared pointer is going to decrement the reference count, or in other words the use count. In this example, we only had one shared pointer that owned the heap object, or in other words that managed that heap object. So the use count was 1, but now it's going to get decremented to 0. And because that is now 0, the control block is going to call the destructor for the managed object. So that is going to get allocated. And then the control block is going to call the destructor on itself. So it's going to do delete this. And then that is going to get allocated as well. Okay, so that was a basic high-level example of the typical shared pointer implementation. In this simple example, in the main function, I have three smart pointers. I have the unique pointer, the shared pointer, and the weak pointer. And of course, I include the memory file for the smart pointers as well. And then what I'm going to do is I'm going to do console output the size of the unique pointer, console output the size of the shared pointer, and then console output the size of the weak pointer. And I'll build around that. We get 4 for the unique pointer, 8 for the shared pointer, and 8 for the weak pointer as well. What this demonstrates is that the smart pointers don't use that much memory, and that the unique pointer uses less memory than the shared pointer and the weak pointer. The only member variable or data member in the unique pointer is the encapsulated pointer, which of course will store the address of the managed heap object. So the unique pointer is the same size as the pointer, whether it's 4 bytes or 8 bytes. It depends on the system. In this case, it's 4 bytes. As I've demonstrated in previous illustrations, the shared pointer encapsulates two pointers. It encapsulates a pointer to the managed heap object and then also a pointer to the control block. Now the weak pointer actually also encapsulates two pointers, a pointer to the control block and a stored pointer of the shared pointer it was constructed from. Next, I want to summarize the makeShared helper function now that we have an understanding of the control block and the basic implementation of the shared pointer. I have demonstrated how to use the makeShared helper function in previous lectures, but here I just want to summarize why it is important and why you would use makeShared if you can instead of doing the constructor for the shared pointer. So the makeShared is going to construct and return a shared pointer that owns an object of the specified type t, and of course we can provide 0 or more arguments as we can with the unique pointer. With the makeUnique, and the helper function is going to infer which constructor to invoke based on the arguments. And also what's useful with this is we can use the auto keyword for type deduction, and you can use the assignment operator, or you can just use the list initialization as well. What are the advantages of this makeShared helper function? Well, as with the unique pointer, we only specify the type t once, which is less typing with automatic type deduction using the auto keyword. Now, if we consider these two statements, in the first statement, that is going to make two separate allocations, one for the heap object of type t and another allocation for the control block. But in the second statement, where we use the makeShared, there is a single allocation for both the control block and the heap object of type t. So it is more efficient to use makeShared than it is to use the constructor for the shared pointer.